All right, let's dive into one of the absolute cornerstones of electronics, the capacitor. The easiest way to think about it, it's like a tiny, incredibly fast bucket made for holding electrical charge.
Have you ever wondered how a camera flash can just BAM! Unleash that brilliant burst of light in a fraction of a second? Or why some gadgets still have a little bit of juice even right after you unplug them? Well, it all comes down to this ability to store energy and then release it in a flash.
And the hero behind that magic trick is the capacitor. At its heart, it's a beautifully simple device. Really, it's just two conductors. Think of them as metal plates, with a little insulating gap between them. You put a positive charge on one plate, an equal negative charge on the other, and that's it. That's a capacitor.
So how does this whole electronic bucket thing work? Well, it all boils down to this one simple, really elegant relationship. The amount of charge, Q, that you can stuff into a capacitor is directly proportional to the voltage, V, that you push across it. And that link between them, C, is what we call capacitance. It's super straightforward. For any given capacitor, if you double the voltage, you're going to double the charge it can hold.
Okay, so we've got this idea, C for capacitance. But how do we actually measure it, What's the unit? Well, it turns out there's a standard unit for it, and even a surprisingly simple recipe for making one.
So the unit is called the farad, named after the legendary scientist Michael Faraday. Now, 1 farad is when you can store 1 coulomb of charge for every 1 volt you apply. And trust me on this, as we are about to find out, 1 farad is a huge amount of capacitance. And here it is, the basic recipe for the most common kind of capacitor you'll find. Its capacitance, C, really just depends on 3 things. A, which is the area of those plates, D, the distance between them, and that little epsilon naught symbol, which is just a constant of nature. You can just think of it as a number that describes how electric fields like to travel through a vacuum. So, if we're using that recipe, how would you go about building a capacitor that can hold more charge? A bigger bucket. It's actually pretty intuitive. You can make the plates bigger, that increases the area A, or you can scoot them closer together, that decreases the distance D. Either way, you get a bigger bucket for your charge. Of course, in the real world, capacitors almost never work alone. Inside any electronic device, they're all teamed up in circuits to get a specific job done. So let's take a look at what happens when they join forces. So there are 2 main ways these guys team up. When you connect them in parallel, side by side, their capacitances just add right up. It's like lining up more buckets next to each other, your total storage capacity gets bigger. But when you put them in series, end to end, the math gets a little weird and the total capacitance actually goes down. The big takeaway is this. In parallel, the voltage across all of them is the same. In series, the charge stored on each of them is the same. Okay, to really see the power of connecting in parallel, let's try a little problem from our source material. Let's say you need to store 1 whole coulomb of charge, which by the way is a ton of charge, and all you've got is a standard 110-volt outlet. How many of those little 1 microfarad capacitors would you have to wire up side by side to get the job done? The answer is an absolutely staggering 9,090 of them. It's pretty amazing, right? By hooking them up in parallel, all those tiny individual capacitances add up, and suddenly this huge army of tiny components can store a really significant amount of charge together. So, okay, we get it, they store charge. But the real reason capacitors are so incredibly important is that by storing that charge, what they're actually doing is storing potential energy. And that's the energy that powers the camera flash.
And here is the formula for that energy, which we call U. It's 1/2 times the capacitance C multiplied by the voltage squared. Now pay close attention to that V squared. That means if you double the voltage across a capacitor, you don't just double the energy, you quadruple it. That is a seriously powerful relationship.
So let's think big for a second. You know a kilowatt hour, right? It's the unit on your electricity bill. So what kind of capacitance would you need to store 10 kilowatt hours of energy? That's a pretty serious amount if you could charge it up to 1,000 volts.
The calculation from our source gives us an answer of 72 farads. Now, wait a minute. We've been talking about microfarads in our electronics, so 72 whole farads? That sounds like an absolutely enormous number. And yeah, that result brings up a fantastic question. We've been throwing this unit around, the farad. But what does it actually represent in the physical world? How big is a 1 farad capacitor, really?
And this brings us to our final section, a really cool, kind of mind-bending puzzle that gets right to the heart of what these units really mean. We're going to try to imagine building one.
Okay, so let's run a little thought experiment. This is straight from our source material. Imagine we take two big metal plates. Each one is 1 square meter. Now, to get a capacitance of exactly 1 farad, how close do we have to put those two plates together?
Well, when you run the numbers using our recipe from before, you get this. 8.85 times 10 to the negative 12 meters. I mean, that is an almost unthinkably small distance.
It's one thing to see a number like that with all its zeros, but it's a whole other thing to actually understand what it means. So let's put this into a perspective that we can actually wrap our heads around.
So on the left, that's the tiny separation our plates need. And on the right, that's the approximate size of a single atom. As you can see, the distance we calculated is more than 10 times smaller than an atom itself.
And that's the big reveal. It is physically impossible. You can't build this capacitor. Why? Because to get the plates that close together, they'd have to literally pass through each other at the atomic level. The farad is, fundamentally, a gigantic unit of capacitance. And that leaves us with one final, fascinating puzzle. If a simple 1 farad capacitor is literally impossible to build, then how in the world do engineers make supercapacitors that can hold thousands of farads in a package that fits in your hand? Well, the answer lies in some very clever geometry and amazing materials called dielectrics, which completely change the rules of the game. It's really a testament to human ingenuity, taking a simple principle that seems almost impossible and engineering it into these tiny, powerful components that really do shape our world. But the secrets of how they do that? Well, that's a story for another time.